All right, so we're moving on, talking about more integration techniques. In chapter 8, we did integration by parts last time. So, and remember, integration by parts, one of the ways I told you could recognize that was if it was a mixture integral. A mixture integral is an integral that has maybe some algebra terms like an x and an exponential term like e to the x times e to the x, or x times ln of x, or x times sine of x, where you have two different types of functions multiplied together. So for this section now, we're mainly focusing, we're back to just plain algebra integrals. And in fact, these are all going to be fractions. So integration by parts is not really going to be your first thought on these, because you would only be wanting to use those on mixture integrals. So we can kind of forget about that for the most part. All right, so if you've got all algebra and you've got a fraction, the first thing you'd want to look for is regular U substitution. And if you've had a chance to look at this one, hopefully you see that this is a really nice one, right? If I just let U equal x squared plus 4x plus 3, du is going to equal 2x plus 4 times dx, which is exactly what we have in the top. So this is just going to be, the bottom is u, the whole numerator is du. This integrates to natural log absolute value of u plus a constant. And my u was x squared plus 4x plus 3. Easy, right? That should be easy right now. Now look at my next one, and it's almost the same, except I changed the numerator to 2x plus 5. And to be clear here, we've been talking about this wishing technique where you get to wish for something. But to be clear here, what I needed to see was a 2x plus 4 times dx, and I had a 2x plus 5. You can't like wish for minusing 1 here. You can't. The only thing you can wish for is multiplying this whole mess by something and then compensating outside. So you can't like wish for minusing 1 here and then adding 1 or something at the end. That's not going to work. So because as close as this is, there's no way I can multiply 2x plus 5 by something and get 2x plus 4. U substitution is out. So the next thing to think about, if that doesn't work, is to focus on the denominator and hope that it factors. And in this case, it does. That factors into x plus 1 times x plus 3. And if it does factor, we're going to now use a technique we call partial fractions. Okay, and so let's talk a little bit about what we mean by partial fractions. Let's think about it with numbers here first. So it has to do just like with numbers, right? If you were going to add, let's say, 1/2 plus 1/5, you've been adding fractions for a long time, you probably can already tell that your denominator is going to have to be 10, isn't it? Why 10? Because we would know we'd need to find a common denominator. You know, this one top and bottom by 2, this one top and bottom by 5, and your common denominator would be 10. And I could certainly, you know, figure out what that numerator is by finishing the problem. But the idea of partial fractions, most of your time spent with fractions was taking two fractions and combining it to one. But the idea of partial fractions is, what if I gave you a single fraction like 8/15, and now what you have to do is try to break this up into the sum of two smaller fractions. So it's like taking a single fraction and thinking backwards. Now, one thing we would know for sure based on the way we add fractions is, what would our denominators be? If we got 15 for our final common denominator here, can you see that our two denominators would have had to be 3 and 5, right? Those are the factors of 15. 15 is 3 times 5. So those would have to be the numerators. I'm sorry, the denominators. And we could temporarily, you know, call this numerator A, call this numerator B, and do some work to try to figure out what A and B are. Okay, so this is the idea of partial fractions, is going the other way, taking a single fraction and trying to think of that as the sum of two or more fractions. Okay, so this is, so we have this single fraction. I'm going to move this even further down. 2x plus 5 over x plus 1 times x plus 3. And what we'd like to do is break this up, because we can't integrate it. We'd like to think of this as the sum of two fractions. And we could tell that one of your fractions would have had a denominator of x plus 1. The other one would have been x plus 3. We'll temporarily call the numerator of this fraction a, the numerator of this one b. And now our goal is to solve for a and b. Goal is to find a and b. So that we could, then the idea is, instead of integrating this fraction, which we couldn't do, we could integrate each of these separately since they add up to this. And those should be easier. Okay, so this is going to be our setup. But to actually solve for a and b, here's the best thing to do. We're going to now take this expression and get rid of the denominators. Just rewriting it here. By multiplying both sides by the lowest common denominator of the whole thing, which is always going to be this. It's going to be x plus 1 times x plus 3. On the left side, they're just going to cancel out, leaving me with just 2x plus 5. On the right side, if I distribute, you can see the x plus 1 would cancel on the first one, so I would end up with a times x plus 3. And for the second one, the x plus 3's would cancel, so I'll have b times x plus 1. Now, from here, there's actually two different methods they'll teach you about, and you should know both of them, about how to proceed to solve for a and b. For a problem like this, I think the easiest way is to do this. This is an equation, and so it should be true no matter what my value of x. So what I'm going to do is pick a convenient x value. I'm going to plug in -3 for x to both sides. So if I plug in -3, that's -6 plus 5 gives me -1. And here you can probably see why I chose -3. This term's going to get wiped out. It's going to be 0. -3 plus 1 is -2b. If -1 equals -2b, I can quickly figure out that b is equal to 1/2. Now another nice number to plug in is -1. 2 times -1 plus 5 is 3. -1 plus 3 is 2. And then this term gets wiped out. So if 3 equals 2a, I can figure out that a is equal to 3/2. So all of this was so that we could find these values, and now we're going to plug them in, and we're going to now be integrating these two fractions, because that was the same as our original integral, with this value of a and this value of b. So we're now integrating a over x plus 1, so that's 3/2 over x plus 1, and we can do these separately or together, plus the integral of 1/2 over x plus 3. And each of these are really simple integrals. If you pull out the 3/2, you're going to be left with just 1 over x plus 1, which would integrate to a natural log of x plus 1. Same thing here. Pull out the 1/2. I have 1 over x plus 3, which would also integrate to natural log. Tag on our plus c, and we're done. All right, so, and what I wanted to say here was, you know, you can, obviously that's a lot of work here, right? There's a little more work here. Because you can do this anytime the bottom factor. So even on my first example, I could have used partial fractions to solve this in the similar way. But you see how much easier it was to spot the U substitution and integrate it that way. So just like with integration by parts, you should definitely give U substitution a fair chance before you jump into it with partial fractions, because you could waste a lot of time. So like this next example, if I was going to try U substitution, I would probably have U equaling x cubed minus 4x squared. Du would be 3x squared minus 8x dx. And this will hopefully clear up another possibly misconception about the wishing technique. Okay, look at I did this on purpose. My numerator is 3x minus 8 dx, which is so close to what I needed to see for du. In fact, it's only off by an x, right? But you're only allowed to wish for constants. I can't wish for an x here to make that look like this and then compensate outside with a 1 over x. I can only wish for constants. So as close as this is, it's not going to work. And I'm left with now recognizing that here I can factor out an x squared. And if the bottom factors, if you've got a fraction where the bottom factors, we're now going to switch over to partial fractions. I just put PFs. Okay. And the idea is we're going to spend a lot of time trying to rewrite this as a sum of 2 or more fractions. So we're going to ditch the integral for a second. We're just going to work with this expression, 3x minus 8. Now, there's one catch on this one. What we want to do is think about fractions that would have this as a sum. And to me, the two obvious denominators would be x minus 4 and x squared. But if you think about all of the possible fractions that could have given me this as a lowest common denominator, you also have to include that there could have been just a regular x to the first. If you think about it, the lowest common denominator of these three is still this. Okay. So this x squared is referred to as a repeated factor because it's x and then another x, right? X squared. And so what it boils down to is you need a term for each power down to 1. Need term for each power down to x to the first. So for example, if this had been x cubed, you would have needed a fraction for x cubed, x squared, and x. You would have had to have 3 separate fractions just for that if it had been x cubed. Okay, but that would be a long one. Although you might see some of those, but that would be a really long one here. So we're going to have for our numerators a, b, and this time we need to bring in a c here. And our goal is to solve for a, b, and c. So I think I'm going to save a little space here. So how we do that now, the next step is to multiply both sides by the lowest common denominator, which again is always whatever your denominator is over here. On the left side, they just cancel. So that leaves me with 3x minus 8. On the right side, the x minus 4's cancel, so I'm going to have a times x squared. For the b term, the x squareds cancel, so it's just b times x minus 4. And for the c term, only one of the x's cancels, right? So that's going to be cx times x minus 4. And just like we did on the last one, I see some nice numbers we can plug in. If we let x be 0, the left side will be negative 8. Whoops, not plus, this is equals. A times 0 is 0. This will be minus 4b if x is 0. And if x is 0 here, this term would be 0 because of that x. So I end up with negative 8 equals negative 4b. B will equal 2. Another nice number I could plug in is 4. 3 times 4 minus 8 would give me 12 minus 8 is 4. A times 4 squared is 16a. That would be 0 because it's 4 minus 4. And this would be 0. So I have 4 equals 16a. A is equal to 1/4. Now, at this point, I've kind of exhausted my nice values for making things equal to 0 here. And so some people would switch over to the other method, which we could certainly do. But we really only have one other constant to solve for. And so what I would do here is just stick with this method. We've only been plugging in these values because they conveniently make things equal to 0. But the truth is you can plug in any x value you want. So if I still have one more constant to solve for, I just pick a random x value. I'd pick something nice, like how about I'd pick 1 maybe, right? 3x minus 3 times 1 minus 8 would give me -5. And remember that you know a and you know b. So a is 1/4 times 1 squared. B is 2 and x is 1. So that's 1 minus 4. C times 1 minus 4. We're going to have to do a little algebra here, but we'll figure this out. 2 times -3 is -6. This is going to be minus 3c. If I add the 6 over here, that is 1. I'm just going to get rid of the 4. Multiply both sides by 4. 1 minus 12c. I move the 12c over here. Divide by -12. Looks like c is going to be -1/4. Okay. So then you would just put these values in to your 3 fractions. That's up here, a, b, and c, and integrate. So we have a, which is 1/4 over x minus 4. Let's just try to do these all together. B is 2 over x squared, and c was -1/4 over x. So first one, if you pull out the 1/4, that's 1 over x minus 4 is an ln. This one's an ln. Be careful here, that's not an ln because it's 2 over x squared, and it's only ln if it's x to the first on the bottom. So instead, we should think of this as 2x to the -2 and use your power rule, where you go 2x to the -1 over -1, right? Add 1 and divide by that. And when it's all is said and done, it's going to be minus 2x to the -1 minus 1/4 ln of x plus, I like to joke here, we usually put plus c at the end, but we've already used c here, right? So, I mean, nobody's going to really care if you did that, but, you could either pick another letter or you could be silly a little bit, right? Maybe put like plus smiley face here, right? Where smiley face is a constant because we've already used c, right? All right. Take a look at your next one here. Check on something. Ah, yes. Okay. Sorry, I had to check on something. Don't have a video for that. Okay. Whoops, that's not what I wanted to do. Okay. So here's another one. I said you should think about U sub. You can try it, but I don't think anything's going to work here if you let U equal the bottom or any part of the bottom here. So let's just go straight into partial fractions. Now, this one's a little bit different in this way. I want to rewrite x plus 1 over x times x squared plus 1. You want to factor it all the way if you can, but notice x squared plus 1 doesn't factor anymore. And this, when you see something like this is called an irreducible quadratic. Irreducible quadratic. It doesn't factor anymore. And so the way it works with partial fractions is we're definitely going to need a fraction for the x and the x squared plus 1. And there's a whole idea here. I don't know, we could spend time later talking about this, but we put, this is x to the first, and what do we put above it? We put a constant. If you think in degrees, that's degree 1, a constant is degree 0. So if you had an irreducible quadratic, the numerator should be 1 degree less than that, which would be a linear function. Remember, linear functions like mx plus b, but we usually use a, b, and c. So instead of mx plus b, we'll have bx plus c. So if you have a irreducible quadratic, what you need is a linear term on top. Yeah. And a natural question would be then, well, what if I have a cubic, right? An irreducible cubic? What happens is a cubic equation, if it was x cubed plus 1 or something, many of you probably know that actually could be broken down. That could be factored. And so it's pretty much going to come down to irreducible quadratics, nothing else. All right, so that's really the main thing, is knowing that's going to be a linear term. Everything else is basically the same in that we're going to try to get rid of our denominator. Left side just cancels. Multiply this in here, the x cancels, so I'm going to have a times x squared plus 1. And for the second term, it's going to be x times bx plus c. Okay. Now I can see, so with what we've been doing so far, I can see one nice value to plug in. Remember, we like to pick things that are going to wipe out terms. If I let x be 0, I can see that 1, 0 squared plus 1. So that's just 1 equals a. And because this is 0, 0 times the rest of this would make that 0. So I've got one of my letters. A is 0. A is 1. I'm sorry. A is 1. Now, there's no more nice numbers that are going to make things equal to 0, at least on the right side. And I still have 2 more letters to solve for, 2 more constants. So at this point, you have a couple options. You can either continue to pick numbers, okay? And it maybe wouldn't be too hard. So maybe if I pick like x equals 1, that would give me 2 equals, remember we know a, so that would be 1 times 1 squared plus 1, which is 2, plus 1. If x is 1, this is going to be b plus c. And what does this actually tell me? If this would subtract over, and 1 times b plus c is just b plus c. So when x is 1, I get 0 equals b plus c. That has 2 unknowns. I'm not going to be able to solve that by itself. But what I could do is always just maybe pick another number. How about, well, how about if I let x be -1? The left side would be 0. A is 1, so that's going to be 1, and -1 squared plus 1 is still 2, plus -1. B times -1 plus c would be -b plus c. And this gives me, let's move this over, -2 equals b minus c. So then the idea is you've got two equations and two unknowns, right? I've got 0 equals b plus c, negative 2 equals b minus c. And that's something you should be able to do, right? You've done that before in your life. Maybe here it's just too tempting. If I just maybe move one over, I can see that b is equal to negative c, and then plug that into here. So negative 2 equals negative 2c. That tells me c is equal to 1. And if c is equal to 1 and I put it right back into here, then I can see b is going to equal negative 1. And I've got all three of my letters. Whoops, couldn't see the bottom part there, though. There we go. Okay. Now, at this point, I want to show you there's another method that we could have used. And it's worth knowing this method. Okay, so we've got a, b, and c. We'll finish off the integral here, but let me talk about the second method we could have done, which you should be familiar with. The second method involves multiplying everything out. So what I mean is, if we pick this back up where we had x plus 1 equals a x squared plus 1 plus x times bx plus c. Move this over so you can see it. Sorry, let me get myself organized. And we already knew a was 1, but let's pretend we didn't even know that. If I multiply this all out, ax squared plus a, if I distribute this x, this would be bx squared plus cx. And the idea here is comparing that this is an equation, so the left side and the right side need to be equal to each other. And so if I compare things by like degrees, like if I look at my, for example, my x squared terms, on the left side, there are no x squared terms. So I could say 0 equals, how many x squared terms do I have on the right side? Well, I have a plus b x squared terms, right? I'm just looking at the coefficients. Like if this was 3 and this was 7, I would say I have 10 x squared terms. Why? Because it's 3 plus 7, right? That's why I say a plus b. Okay, I can't solve that. That has two unknowns. So let's now just look at my x to the first terms. On the left side, I have 1, right? Because it's 1x, so I have 1. On the right side, the only linear term here, x to the first, is just c. So now I know c. C has to be 1. And then finally, if I look at my constants, on the left side, my constant is 1. On the right side, the only thing that would have been a constant here is a. So now I know a is 1. And hopefully you can see if you knew a was 1 and plugged it right back into here, you would then know b has to be negative 1, which was the same values we got by plugging in here, right? We got a was 1, b is negative 1, c is 1. And you'd probably agree that this seemed a little bit easier, right? But the truth is that there's times this method becomes really, really awful. And you should just be plugging in x values like we did before, and then vice versa. There's times when plugging in x values is bad, and this is really the easier way to go. So it really is to your advantage to know both of these methods. And there's times I actually do use both of them in the same problem. Okay, let's finish this off. So remember, way back when, we're going to be putting our a, b, and c back into these two integrals here. So we're going to be integrating a over x and then plus bx plus c. So it'd be negative x plus c was 1 over x squared plus 1. And I'd probably do these as two separate integrals because this one's really easy. That's ln of absolute value of x. This one's a little bit tricky. I can't remember if we've done one like this, but you know, U substitution doesn't appear to work as a whole here because the derivative of the bottom is just 2x. But this is one where if you actually just split this up, So you could think of one integral as the integral of negative x over x squared plus 1, and the second integral 1 over x squared plus 1. This one, hopefully you recognize as a U sub. Let me get a drink of water here. Finish these off. We could always pull this negative out first and then just wish for a 2, compensate with a 1/2 on the outside. And this integral will turn into negative 1/2 du over u, which is negative 1/2 ln of u, but my u was x squared plus 1. I got to bring this down too. And then, of course, this last one is just arctan or inverse tan. Well, let's see. We already used up plus c, so maybe we'll do I don't know, tree, where this is a constant. So you got to make your graders laugh, right? If they're grading your papers and you can put a smile on their face, they're probably going to maybe be a little more forgiving in terms of taking off points. Just suggesting, right? I'm trying to give you ways to get ahead. Okay, let's see. Yeah, I'm going to skip that one. I'm going to go to number 6 here. So another thing to watch out for, something we talked about, I think even just the last time we met, that if you're integrating a fraction and the degree of the top is greater than or equal to the bottom, even if they're equal, you must first rewrite with long division. So here, I'm going to have to take x squared minus 4 divided into x squared minus 1. I don't know, this isn't even really a long division. It's a kind of a short division. If I put a 1 there, multiply that down, and subtract, I get this to cancel, which is why I chose a 1. I wanted that to cancel. And I have -1 minus -4 is really plus 4, gives me a remainder of 3. And so remember how that works is that means I'm going to have 1 plus my remainder over x squared minus 4. And this is just this rewritten. And so what I'm now left to integrate is the integral of 1 dx plus, you can bring out the 3 or leave it in there. It doesn't really matter. 3 over x squared minus 4 dx. This is easy, right? This is just going to be x. And this, there's no way a U substitution is going to work. So guess what? We're going to have to rewrite this one, the bottom factors into x plus 2, x minus 2. And we're going to have to use partial fractions just for this part right there. This is probably a good time if you're watching the video, just pause it. See if you can work out this partial fractions integral. And then hit play when you're done. Okay, there's my setup. I'm going to clear the denominators. I know what I'm going to do. I'm going to forget that x. So I got to remember that x is there because we're working on this right now. We've already integrated that, but let's try to remember it. That cancels. 3 equals x plus 2's cancel. A times x minus 2 plus b times x plus 2. I think it's easier if you've got definitely two obvious numbers to plug in and make these equal to 0. That's the best method. So I'm going to let x be 2 first. This is 0. Or b equals 3/4. And then I let x be negative 2. It's going to be negative 2 minus 2 minus 4a. That's 0. Can't see that. And so let's remember this x. So we still had that x there. But now we're going to integrate these two fractions with a being negative 3/4. And each of these are just ln's. Minus 3/4 ln of x plus 2 plus 3/4 ln of x minus 2 plus c, or plus whatever your favorite thing you want to put in for a constant term. Okay, and then just a couple more here. Maybe we won't finish these, but just I just want to remind you now that you have this new technique, and this is similar with integration by parts. It may come up. It may not start out as partial fractions. It may just develop into partial fractions. So you may not be jumping into it, but you just have to remember that that's always an option when you have to integrate. If you end up with something with a fraction where the bottom factors. Okay, so like this one here, partial fractions would not be on my mind here because the bottom just has one term, okay? Integration by parts would not be on my mind because this is not a mixture integral, okay? And I can't overemphasize that enough. I'm not saying that integration, you could not integrate this with integration by parts. I'm sure there's a way, but what I claim is because it's not a mixture integral, there's always I think a better way. So I'm not going to say not, but let's not use integration by parts. Okay, so what does that leave us with? Well, maybe U substitution. And I think I showed you one before where if you've got a square root function in there, there are times it's weird. It doesn't seem like it's going to work out, but letting u equal the square root part gives us options. So I'm going to let u equal the square root of x plus 1. Before I do the du, because this is kind of messy, I'm going to square both sides. I think I've done a problem like that where we've seen it. And then I'm going to do the du from here. So the derivative of the left side is 2u du. The derivative of the right side is just dx. So let's see where we're at. This root x plus 1 is u. I actually have it solved for dx now, right? Dx is 2u du, so times 2u du. Now I need a replacement for this x in the bottom, and we've also seen that technique where if you can go back to one of your two statements before I did the derivative and solve for x would be u squared minus 1. I could put that in to the denominator. And everybody has been accounted for, and this leaves me with the integral of 2u squared over u squared minus 1. And so I like this actually. This is good review. So how would I integrate this? Well, I know the bottom factors into u plus 1 times u minus 1. But what I'm also seeing is what we saw on the previous problem is the degree is the same, huh? So what I would first have to do, and I think I'm going to just, to make this video not super long here, you would first want to rewrite with long division. Well, okay, I guess I need to show you that. Okay, here's why, because I want you to see what you're going to be left over with. So if I want to cancel out a 2u squared, so I'm going to put a 2 there. That gives me 2u squared minus 2. 2u squareds cancel out. Nothing minus negative 2 gives a remainder of 2. So this would become 2 plus 2 over u squared minus 1. So we did the long division. Now we have to integrate 2 plus 2 over u squared minus 1. And notice that factors into u plus 1, u minus 1. This would be with respect to u. So the integral of 2 with respect to u would be 2u. And this is where I think I'm going to just let you try this on your own here. This would become partial fractions to finish off this last part. Okay. And then don't forget, when you're done with all of this, we have to put it back in. What did u stand for? When after you finish your partial fractions, make sure you put in root x plus 1 for all of your u's. Okay, and then another one. Now this one is a mixture problem, right? It's got an ln and it's got an x squared, and u sub doesn't appear to work out. So this one, absolutely, if u sub doesn't work, I would jump into integration by parts. And remember, integration by parts, you need to have a product. So I need to think of this as ln of x plus 1 times, I would have to have this up x to the negative 2. So my u, which of these is going to become simpler when I take the derivative? Or if you use Lyautey, u would be x plus 1. dv is x to the negative 2. The derivative of this is 1 over x plus 1 times dx. And your antiderivative of x to the negative 2 is x to the negative 1 over negative 1, or negative 1 over x. If I plug into my formula, uv minus the integral of v du so that's going to give me, let's just put this, rewrite this one as negative ln of x plus 1 over x. We'll pull out the negative here. And see what we're faced with now. We did integration by parts, and we have this integral, which has 2 individual factors. So here is another one where, to finish this off, you would want to use partial fractions with this. Okay, I'm not going to do that. That's good practice for you. I think it's more important to see how it's going to play out. All right, one last one here. Because we're talking about fractions, I want to remind you, I think we covered one like this before, but how do you know when to use partial fractions? It's got to be a fraction, right? And you should be thinking about the bottom factoring. But what if the bottom doesn't factor? If the bottom doesn't factor, okay, recall, I think we did one of these in section 8.1, it may be completing the square. And what you're going for here, if you're going to complete the square, what you're going for is you're going to try to make this look like an arctan. You're going to try to get it to be 1 over u squared plus 1 du. Okay, obviously that doesn't factor. So this would be 1. So what I want to do is think about a number I'm going to add here to complete the square. We'll bump this 14 out of the way. The number that completes the square, 6 over 2 squared gives me 9. Since I added 9, I'm going to immediately subtract 9. X squared plus 6x plus 9 is x plus 3 squared. Minus 9 plus 14 is plus 5. Yeah, I made this one intentionally even messier in case you get one like this. So that's starting to look more and more like this, but I need to get this to be 1 here, not a 5 here. So what I like to do is I'm going to just divide everybody by 5. I can pull out the 1/5. This is now just dx 1. And this is now plus 1. And then here's the trick to this whole thing when it's a messy arctan. I have to now think of this whole thing as something squared. So I need to think of this as x plus 3. Are you ready? If this whole thing's going to be squared and I get 5, I have to think of this as root 5 squared. All right. If I square this, I'm going to get that. So now it's got the right form if I let u equal x plus 3 over root 5, also known as, if I split this up, 1 over root 5 x plus 3 over root 5. It makes the du easier to see. The derivative of that is just going to be 1 over root 5, which I need to wish for. Right, I don't have that, so I need to wish for a 1 over root 5. Compensate outside with a root 5 over 1, or just root 5. So now I have root 5 over 5. This is now du u squared plus 1. And that is an arctan. Or tan inverse. I'll write it both ways. How's that? Tan inverse or arctan of my u, which was x plus 3 over root 5. Yeah. All right, so that's it for now. Let me know if there's any questions. You can email me. Or if you see any problems with mistakes I made, please let me know about those as well. So thanks for watching. We'll see you next time.